It's cancel, and then you're just left with 4 by 3 by 2, which is 24, 5 squared, which is 25. So 24 over 25 is just 96%, which is what you were asked to show. Right? So that question wasn't too hard. Now this one is harder. The next one is question 9. It's a bit of, I'm jumping around a bit, but it's harder in the sense that you need to do some more difficult integration, and well, just the calculation's a bit tedious. So I haven't actually done the numerical side towards the end. I've just given you the sort of strategy, I guess, right? So the problem is you're given a hydrogen atom, and you're told that the electron in the hydrogen atom is in the ground state, right? It's in the lowest energy state, and so you're asked to find what's the probability that that electron is inside a sphere of radius 10 to the minus 14 of a meter. Now I've just used the letter big K here to represent 10 to the minus 14 of a meter. Okay, so what's the probability that that electron is inside this very small sphere? You know, it's only a little bit bigger than the nucleus, right? It's very, very close to the nucleus. The nucleus tends to be of 10 to the minus 15 of a meter in size, roughly. Well, the smaller ones. Okay, so what's the probability that the electron, if you measured it, if you looked at it, would be found inside that sphere? Well, it's just the probability density times the volume, right? Well, now since the density varies with the radius, you're going to have to integrate. So you'll integrate over 0 to this radius, 10 to the minus 14, which I label as K. Okay, so over the range, this is for your R, the radius, from 0 to K. Now, U0, this is your wave function. This is from the theory. Go back and have a look if you like. This is the expression we got for the ground state. You know, the lowest energy wave function, which is this, right? So square that. That gives you the probability density. This is just an amplitude. The wave function is an amplitude that you square to get the probability density. That's Born's interpretation, right? Now 4 pi r squared is the surface area of a sphere, and you multiply it by a little thickness. So this expression here is your kind of dV, the small volume, right? The surface area times the thickness of that area. So think of it as like an onion. So this is the small dV, the small volume in that onion of radius r. Okay. Well, we know what U0, the ground state, is. It's this. So just square that. So that's where this 2 comes from. Okay. And if you're squaring this, so you get a pi a0 cubed. This a0, what's that? It's called a Bohr radius, and from the theory it was this. Okay, so that's your a0, and it's has dimensions of length. So it's well, just from the label Bohr radius, so you know that it's a particular radius length. Okay. Alright, so the pi's here cancel. You can take the 4 over a0 cubed outside, they're just constants. And so this integral simplifies a bit to just integral 0 to k e to the minus 2r over a0 r squared dr. Now integrating that is non-trivial, but in the textbook, in chapter, there are a table of useful integrals, if I can find it quickly. Appendix E in the text, I'll show it to you. Useful integrals, and this integral this integral is listed there. Well, in more general form, they give you the general form for when this power here is n, but I've written it out here for when n is 2. Okay, so the indefinite integral here is of this form. Okay, so just use this indefinite integral, but between the two limits. So it'll be this when r equals k minus this when r equals 0, and that will give you your probability. So it just became number crunching, and you'd need a calculator or computer to do that for you. All right, and a similar comment for the next part of it. Now, the second part of the question is, you're asked, what's the probability of finding the electron, so it's in the ground states, that's lying outside the sphere of diameter 2 times the Bohr radius. 2 A0, 2 of these. All right. So, well, can you see? It'll be, now it's got to be somewhere, right? It's got to be somewhere in an infinite sphere about the nucleus. So the probability of it lying outside this range, like that's 2A0, and it's here somewhere outside, that probability of it being outside will be 1 minus the probability of it being inside. Okay, so your k here is now just 2a. So this probability here is what? It's the probability that the electron is found inside this sphere of radius 2a. Okay, so so the probability of it being outside would be 1 minus this. So to calculate this, you just do the same thing as you did here, with one exception. And instead of k being 10 to the minus 14, it's just 2a. So it'll be 2 whatever this. You have to work out what this is. Right? So a bit tedious. So you need the values of, like, Planck's constant, the mass of the electron, the charge of the electron. All those are also listed conveniently for you. That's in Appendix D, called Useful Quantities. And here's okay. So you have a list of these constants, physical constants. They can give you what h bar is, although in h, but h bar, and the mass of the electron and the charge of the electron. Right? So you know what? So you can calculate what A0 is, and then twice double it, and that'll be your upper limit, and get your answer, get some numerical answer. But it involves calculating all this stuff. I'm just giving you again the strategy, right? The theory. The numerical stuff is rather dull, so I try to avoid that kind of stuff. All right? So that's the end of the problem-solving portion of this lecture, and hence the end of lecture 4 and chapter 4. And chapter 4 is a really substantial chapter, a large number of questions, so try to do a lot of them. And it's one of the big chapters of the whole text. Another one in 2 chapters' time, chapter 6, on the principles of quantum mechanics is coming up. And those pretty much the heart of the text. They're like angular momentum is an important one with spin and so forth. But so chapter 4 was one of the substantial chapters of the text. So until next lecture, next chapter.